morning, everyone. My name is Walt Hubis. I'm a storage standards architect with Fusion.io. But the purpose of my talk today isn't really so much to do with Fusion.io and what we're doing. It's more to talk about the software architectures that NVM is now beginning to present to applications, and probably in areas very close to what we've been talking about here. One of the issues that comes along with the proliferation of these new interfaces and new ways of approaching storage has got to do with standardization. So if everybody's got different interfaces and everybody's in changing applications and all of the things that they're doing, it's almost pointless. So I'm here to talk about largely the SNIA NVM programming group. This is a group that we're very active in. We believe will help to standardize some of the interfaces and some of the new techniques that you can take advantage of when you start looking at some of these new classes of storage. So first, let me go ahead and set the stage a little bit. To begin with, of course, you know, this is sort of an evolution of how this group came to start working on this stuff. It started out basically by putting SSDs into disk drives as a cache, as an accelerator. From there, we go to just a basic SSD, so flash as a disk drive. And then moving forward, finally, flash as memory that could typically go on a PCI bus. So this is kind of where it's been going. And the architectures are pretty straightforward. You know, the flash as a disk, you have the usual host CPU that either has a RAID controller or some sort of interface down to that storage, and typically to aggregate and to get the storage space, the RAID controller aggregates that stuff. And of course, the problem is there's a lot of different commands that need to happen there, and there's a lot of different layers. When you look at flash as memory, it's a much more direct route. There's fewer layers, and I think several other folks have spoken to this before, that latency goes down and access times go up rather nicely. I think the previous speaker even mentioned that there's a lot of stress. You know, SSD, because of its inherent capabilities in terms of speed, puts a lot of stress on these interfaces. So the less interfaces you have, the better off you are. So there's been a real trend to start moving towards flash as more of a memory device than a traditional storage device. This is an example of that. Again, I'm using some specific information from Fusion.io, but I think it's generally pretty applicable. One of the problems you have with SSDs is you end up with very inconsistent performance over time. You end up with these latency spikes that are based on trying to talk to multiple drives. You have locking issues, you have stack issues, you have threading issues, all sorts of stuff like that. Whereas whenever you can just directly access it through a simple, straightforward interface, you get much more consistent throughput and much more predictable latencies. The other thing that this class of storage gives you is it also gives you the ability to do these what we call native APIs, and I think several other folks have referred to them here. You have certain primitives that you can implement actually on the storage and take advantage of the architecture of the NAND flash. So the evolution of this, again, the SSD, is pretty straightforward. Typically a block device through a file system or through some kind of a network. And then you have flash as a block drive, which is, again, very similar to what you'd expect to see for a disk drive. But what you're able to do is you're also able to implement cache, and I think a lot of folks have been doing this already, as a transparent cache. So you use it as a caching device between, say, for example, rotating media or slower devices. But where it starts to get interesting is now if you have direct access. So what you're able to do in this particular case, I'm showing some sort of application that has some extensions in it. So you're doing something in the application to enable this, but it allows you to talk directly to the NVM storage device. You can also you can access that either directly as load store operations, or you can configure that as a file system. The FTL, of course, being the flash translation layer that actually manages how data gets written to the non-volatile memory. And then finally, there's the concept of memory semantics. And there's a whole group of different primitives, different things that you can do to enable this. Really, there's a couple of distinctions here. One is there's a load store process, as well as you can also access that as a native file system. So in other words, you bypass largely the file system. The FTL in this case presents produces file semantics that you can then use to access that flash quickly. So across these different kinds of access, there's different sorts of semantics. So for example, for I/O, I mean, this should all look pretty familiar to, pretty familiar to everyone. Open, read, write, rewind, close for tape, disk, SSD. But what you're able to do down here in the memory, when you start looking at this as non-volatile memory, there's some basic kind of things you can do. You can do atomic writes, you can do conditional writes, and all kind of different functionality that you can do that takes advantage of kind of the logging file systems and things that you have to implement in a flash device. So this is just a sample case here of, for example, an atomic write. These are typically used for database transactions to assure the ACID qualities of that database. In other words, make sure the writes are durable. And the point is that you attempt to do a write to one of these devices, and either it will all fail or it will all succeed. There's no in between. So this allows you to get rid of some of the logging writes you'd have to do in a database. Again, this is just one example of the kind of things you can do. So we have all of this new technology and all of these very fast devices coming online, and the SNIA group and a group of folks in the industry agreed to get together to try to define exactly what it is that these new technologies offer and how we refer to them. In other words, kind of come up with a standard terminology and a standard methodology for using these new features that we have in these storage devices. So one of the things that we saw quickly was that these features are outgrowing rather quickly existing models. Furthermore, sending block read and writes, especially down a lot of the traditional transport methods, is becoming highly inefficient, especially as the capacity of these NVM devices grows and the speed grows. The NVM technology itself is also inherently evolving more as a memory device at this point than it is as a storage device. So there's a fundamental need for a new model here, I think. And one of the goals here was to have industry collaboration across the board so that common methodologies, common terminologies can grow out of this. And so what ended up happening was the SNIA NVM programming technical group was created in 2012, last year. Now, one of the reasons why like I said, I'm referring to some of our Fusion IO stuff here is the NVM programming technical work group is fairly new. We don't have anything publicly published yet, so we're still under some NDA kind of constraints of SNIA. But it's open membership to anyone that really wants to join, so you can join that group. I'm just using this as an example. This is not, I don't mean to represent this as the model that the NVM group is using at this point in the game, but it's, again, we feel that it's very similar and we're fully supporting that. So the charter of this group is to develop specifications for programming models, actually. So we're not looking at exactly how things get implemented within the hardware or even within the drivers and so forth. But what we want to do is we want to have programming models for applications and various OS components that would use these kind of devices. We have extensions in this for block access, file access, and memory access. And the operating system APIs themselves are a topic that we're really not going to address. So what we're trying to do here is come up with a specification that does not specify an API. So we're defining the programming model. We're not going to specify precisely how that programming model gets implemented in an API. Some of the things that we're looking at this point in the game are discovery of devices, how you discover, in a standard way, how can you discover a device, what are their characteristics, what kind of features do they support, And a good example of that was atomic rights, things like that. One of the things that we want to be able to do is to be able, since this is a memory model, want to be able to assign some portion of an NVM to a memory address, map it into some memory that an application can access. And one of the issues, of course, with that is when you go across reboots and you try to remap this region that is non-volatile, so it's like a file, remap it to a new region in memory, there's issues with how do you handle addressing. How do you make sure that if you have links in there, absolute links and so forth, that they all work correctly. And then finally, how to read and write to NVM. NVM devices have a broad variety of ways that they can be written to, that you, for example, might want to sync them, the way they're cached, all of those things. And that's one of the goals here, is to define a methodology and a process for how you commit those changes and how you assure durability and consistency with these devices. So some of the things that we're excluding, okay, explicitly is one of the things we have to look at. We're operating in terms of some kind of a kernel or some kind of an operating system. We have some environment, and a lot of times those devices, those constraints of that will impact us directly. So some of them we just defer these to the kernel or to the operating system, whatever it is in particular that we're using. Some things like events, software installs, access control and ownership, things like that, permissions. Typically, we don't even touch in the group. And there's also vendor unique behaviors as well. I might also add device management. I mean, management is a very individual kind of function for all of these kind of devices, configuration, that sort of thing. So this particular group is not going to be involved with that. As well as any kind of vendor unique behaviors, you know, the maintenance, the grooming, all of those kind of things that have to happen when you have a flash device. I'd further go on to say that in addition to flash devices, the goal of the specification is to make it broad and generic enough that it doesn't have to be flash memory specific. It could be any one of a series of new technologies that are coming to market. So right now, the group is meeting every week. We have weekly meetings, and we have face-to-face meetings roughly quarterly, where we get together for 2 days and really define the spec. If you're interested in attending, please don't hesitate to contact me. I can give you information about it, point you to the place. Right now, we're working on a series of use cases and actions that define what the actual actions that you have to take are. And as well, one of the more challenging parts of this is actually a glossary. Terminology for NVM devices varies all over the place. So one of the big goals of this is to define consistent terminology across the industry. And our deliverables is TBD, but broadly, we're looking to have something out this year for public review. So this work is also going on not only in the NVMP group, but we also have a lot of work going on of standardization of some of the features in NVM right now, largely happening in the T10 organization. This may migrate to other places, but T10 SCSI is largely a place now where we're also beginning to see atomics and some of the other features start to migrate now down into block level interface devices and so forth. So we have proposals in process now within T10 to actually get some of these new NVM capabilities into place. And that is all I had. Are there any questions? Okay, great. Thank you very much.
Thank you very much,
Appreciate
Walt.
it.